Today we will discuss the topic centrifugal pendulum absorber in vibration engineering. In the undamped dynamic vibration absorber system that is fully effective only at a particular frequency for which it has been designed. In the torsional system, it is possible to use a dynamic vibration absorber of a pendulum type that is effective at all speeds of rotation of the system. This is the pendulum or centrifugal pendulum type absorption that is shown in the diagram, that, that is centrifugal pendulum absorber, and in which a pendulum that is PB that is shown in the diagram and length L is attached to the rotating member at point V, which is at the radius R from the center of rotation O. The mass of the pendulum bob is M and the string is assumed to have negligible mass. The pendulum is subjected to centrifugal force which is much greater as compared to the gravitational force, so that the latter is considered negligible. The rotating body rotates with a angular velocity of omega, and due to this rotation a centrifugal force m omega square r is experienced by the pendulum. In this diagram you can see that a rotating body is here and the center point is O. The radius of the radius of this body, that is OP, and the PB, that is the pendulum. We can understand earlier. The pendulum PB, the point B, makes an angle beta from point O, and the point O makes an angle from the point B is alpha. If there is mass of the body m and the rotation is omega, then we find that the centrifugal force is m omega square r, and the two component of omega square r, that is m omega square r cos alpha and m omega square r sin alpha. Let us assume that at any instant the pendulum is displaced from the radial line by a small amount theta. The bob or mass at the tip of the pendulum is then at a distance r from the center of rotation O and is subjected to a centrifugal force of F is equal to m omega square r. This centrifugal force that is acting along the OB, this force has one component along the pendulum lines and other perpendicular to it. The latter, m omega square r sin alpha, is the restoring force and has to be taken into account in the differential equation of motion for the oscillation of the pendulum. Here, alpha is the angle between the pendulum and the radial line OB. The differential equation of motion for the oscillation in case of pendulum is given as that I theta double dot is equal to minus f sin alpha into L. We know that I is equal to ml square theta double dot is equal to minus m omega square r sin alpha into L. We know that in case of mass of string is also considered, then the I is equal to m plus capital M by 3 into L square, where m is the mass of the string, capital mass that we have considered. From the above equation, we get, by dividing the ml square, then we get the value that theta dot plus small r by capital L omega square sin alpha is equal to 0. By applying the sine rule on the triangle that is OPB, that is shown in the diagram, then we get r upon sine alpha is equal to small r upon sine 180 minus theta. Then we get r sine alpha is equal to capital R sine theta. Substituting the value of r sine alpha from the above equation in the equation, that is theta double dot plus r by L omega square sine alpha is equal to 0. For the small values, we know that sine theta lump sum equal to theta. Then the equation becomes theta double dot plus r by L omega square theta is equal to 0. The above equation for the pendulum is that of the simple harmonic motion and its natural frequency. By comparing the equation, that is theta double dot plus omega square x is equal to 0, then we find that the natural frequency omega n is equal to in root capital R omega square by L, that is equal to omega in root R by L. Or the natural frequency in cycles per second is given by, we know that omega n is equal to 2 pi fn, from where the fn is equal to omega n upon 2 pi is equal to, by putting the value of omega n, that is omega root r by L upon 2 pi, then we find the value of fn, that is equal to capital N root capital R by capital N. Here is n is equal to revolutions per second of rotating body is equal to omega upon 2 pi. From the above equation, the principle of working of the centrifugal pendulum absorber can be seen. It is stated as the natural frequency of the pendulum absorber is always proportional to the speed of rotating body. Then we can say that the Fn is directly proportional to the capital N. If we remove the proportional sign, then we get a constant that is equal to root capital R by L. The usual torsional system receives a certain number of disturbing torques per revolutions. The number of these torques per revolution is known as order number of the system. A two-cylinder engine working on a 4-stroke cycle has one disturbing torque per revolution, and its order number is 1. A 4 and 6 cylinder engines working on 4-stroke cycle have order number of 2 and 3 respectively. A pendulum absorber is designed to eliminate or reduce the torsional disturbances of a particular order number. If several order numbers are present in a system, several pendulum absorbers are required. That is all about the centrifugal pendulum absorber. that we have discussed. Thank you.